welcome to our YouTube channel. This is Aram. So in this video, we are going to discuss about the singly reinforced beam sections by using working stress method. So we already seen that there are two types of sections. One is singly reinforced and doubly reinforced sections. So singly reinforced is nothing but we have in a beam we have two sections. One is compression zone and tension zone. The reinforcement provided only at the tension zone is called as singly reinforced sections. So here some of the stats for singly reinforced sections. So in a simply supported beam, the tension zone is generally of bottommost portion. But whereas in cantilever and fixed portions, the tension zone is at the topmost portion. So the reinforcement provided simply supported beam at the bottommost and the reinforcement for cantilever and fixed at the top. And some of the requirements for simply reinforced sections. So these are the places we can go for simply reinforced sections. So first one, when there is no restrictions on breadth and the depth of the section. So if there is no limitation on the breadth we are taking and the depth we provided, so then we can go for single reinforced section. And the second one is there is no reversal of stress. So if it is a compressive stress, the prolonged time it should be compressive in nature. If there is no reversal in stress, we can go for singly reinforced section. And if the load acting externally, it won't be too large, then we can go for singly reinforced sections. And if there is no architectural considerations needed, and in some cases where for acoustic purpose we need to go for some extrude portions of the beam. So in that cases we need to add some additional stresses. So in that portion we can't go for single reinforced sections. If there is no consideration of architectural purpose, we can go for singly reinforced sections. And generally here we are going to discuss a working stress method. So in the working stress method, generally it's uncracked sections. The bending moment, the permissible stresses lesser than FCR lesser than 0.7 root of FCK. And for bending tensile strength, it is greater than equal to cracking stress. So this should be satisfied for singly reinforced sections. And because of tensile zone itself, it carry the total permissible stress, then we can neglect the concrete at the tensile zone. And last one, that in a cracked section with the working stress method, it is based on transformed sections, which is nothing but the area of the concrete which is equal to M into ASD. So we are considering this in a singly reinforced sections by using working stress method. There are some of the assumptions which was followed in singly reinforced sections by working stress method. So first one is plane section normal to the longitudinal axis remains plane after and before bending. So why is that? Should be elastic in nature. So the section, if we are providing that external load should be linearly varying, should be normal to the longitudinal and remain plane before and after bending. It should not be deformed any other shape. It should be linear in nature. And the second point, the concrete in tension zone is neglected. So we saw in the previous introductions. So the concrete in the tension zone is neglected. So we only consider the steel in the tension zone. So not in concrete. Third point, the bending tensile strength developed in RCC section is resisted by steel reinforcement only. So these 2 points are interrelated. So in a tension zone, we only need to consider the reinforcements. So we doesn't need to consider any kind of concrete in tension zone. And the fourth one, the stress strain relationship on concrete as well as steel is zero at neutral axis. So the stress strain relationship should comes at the zero at neutral axis at center. So and the maximum at the extreme ends. So both compression and tension extreme ends it should be maximum, and at the neutral axis it should be zero. And next one, the bond between the concrete and the steel is perfect. Hence the strain compatibility is applicable. So strain compatibility is nothing but the strain in concrete compression zone which is equal to strain in tension zone. So this is called as compressibility relation. So whereas because of it is having proper binding, so there should be no stress variation between compression and tension zone. So there should be equal stress in the strain in the compression and tension zone. And sixth one, the modular ratio used in analysis, which having the expressions of 280 by 3 sigma CPC, where sigma CPC is nothing but the maximum permissible compressive strength of concrete. It is respective of the grade of concrete. Sigma CPC can be calculated from 1/3 of FCK, where the characteristic compressive strength of concrete at 2080. Next, the last point, last assumption is nothing but that working stress method produces large cross-section dimensions because it is having low moment resisting factor. The reason why is that it is having large factor of safety, then the moment resisting factor is getting lower, then the cross-section dimension is getting higher. So we saw in the introduction video itself, working stress method having large depth of sections. This becomes the section uneconomical. So same here, propose that it is having low moment resisting factor, hence the section cross section dimension should be higher. Some stress strain drawing, pictorial drawing, which shows the relationship of the single reinforced sections. So here the beam, which is having both compression zone and tensile zone, and the reinforcement provided only at the tensile zone. So the FAT depth is nothing but the extreme end to the center of the bottom or tension zone reinforcement. This is called as the effective depth, and this is the stress drawing of single reinforced sections, and this is a transform sections which was we talked in the assumption part. So we have to consider some transform portions for getting better binding purpose. So transform nothing but the area of the concrete which is equal to m into ASD, and already we seen that at center the stress value becomes 0. At neutral axis the value of stress is 0. So here it shows that, and the bottom and top portions the value of stress is getting higher. So the FCB value and the FSD value is higher, whereas at centroid the value of stress becomes 0. So this is the whole pictorial drawing which represents all the some assumptions. And here in tension zone there is only considered reinforcement part. There is no concrete in the tension zone, which is our assumptions. So we have to neglect the weight of the concrete in tension zone. We only consider the area of the steel in the tension zone part. Here some of the important expressions which we have to carry out in a single reinforced section. The first one is depth of the actual neutral axis. So neutral axis is nothing but the exact center portion of the compression zone and tension zone. So the depth of the actual neutral axis, which was getting the expression of P into XA square divided by 2 equal to M into AST D minus XA, where B is nothing but breadth of the beam, XA is nothing but actual neutral axis, and M is modular ratio 280 divided by 3 into sigma CBC, and ASD is the area of the steel, and D is the effective depth. So with the known values, we can substitute all the known values, we can get the value of XC, and in vice versa we can get the value of ASD also with respect to these expressions. And the second one, the compression force. So this is getting the expression of FC equal to half of sigma CBC P into XC. So where sigma CBC is nothing but 1/3 of FCK, and B value is nothing but the breadth of the beam, and XA we can calculate from these expressions and substitute the values, and we can get the value of compressive force. And for tensile force, FST equal to sigma ST into AST. AST nothing but the total number of bars into 8 pi/4 d square diameter square. We can get the value of AST, and the sigma ST value So we already know that the sigma st value we can calculate divided by Fy divided by the factor of safety. So here the factor of safety is nothing but 1.8 for steel. So 0.87 Fi. We will get the value of 0.87 Fi. We are substituting these values and the sigma st into AST. Next, the lever arm value. Lever arm is nothing but the compression of the distance between the reinforcement of the compression zone and the reinforcement of the tension zone is called as the lever arm. So here the lever arm value we can express by the effective depth minus actual neutral axis divided by 3, and the moment of resistance the most important, so which we have to carry out, and then with the respect of moment of resistance alone we can calculate the area of the steel what we are required. And for that motor set we can calculate it in two ways, with the use of compressive force and with the use of tensile force. First of all, for compressive force we can consider moment of resistance equal to half into sigma cbc b into xa into d minus xa by 3 force into distance. This is compressive force and this is a tension value, the distance value. Next, for tension force, respect of tensile force, moment of resistance equal to sigma st ast into d minus xa divided by 3. And next one, the important one, so the depth of critical neutral axis. Critical neutral axis is nothing but beyond that there will be some deformation will happen. So that portion is called as neutral axis, critical neutral axis, and it can be obtained from the expression of m into sigma cpc by sigma st divided by xc divided by d minus xc. Here m is nothing but modular ratio. We can found this by 2 by 3 sigma cpc, and sigma cpc we already found with respect of 1 by third of fck, and sigma st value, so Fi divided by factor of safety of steel, and xc that we have to consider, and d value effective. So all the substitute all the values. So finally we can obtain the value of critical neutral axis, and we can express this xc equal to k into t, where k is nothing but neutral axis depth factor. So the value for k, expression for k is nothing but 280 divided by 280 plus 3 into sigma st. So it can be expressed, so by interpolate all the values we will get the value of this thing. So k equal to 280 divided by 280 plus 3 into sigma st. And next one, the percentage of tension steel, how much percentage we need to carry out for the proposed beam. So in that we have to form the expression of, so compressive force and tensile force. So both by comparing both the forces, we'll get the percentage expression for percentage is nothing but P equal to K into sigma CPC divided by 2 into sigma ST in 100, where sigma CPC 1 by third of FCK, K value 280 divided by 280 divided by sigma ST, and value of sigma ST we already know that. And the last one, lever arm. The lever arm already told that you can find the lever arm two ways, T minus XA by 3. So by knowing all the expressions, we can suggest the lever arm also can be considered by using these two expressions, Z equal to J into D, where J is the lever arm factor. So J equal to 1 minus K by 3. K is nothing but neutral axis depth factor. So substituting all the values, finally we can obtain the value of lever arm. Whenever we say about single reinforced sections, there are three different sections available. One is balance section, second is under reinforced section, and third one is over reinforced section. Generally, over reinforced sections we do not consider for single reinforced sections, but for theoretical purpose we have to consider the over reinforced section here. So what is balance section? Balance section is nothing but the neutral axis which is exactly laid at the center of compression and tension zone. So we can say the critical neutral axis, which is nothing but the neutral axis depth. Beyond that there will be a failure, either it can be compression, it can be tension. So that is called as the critical neutral axis. Actual neutral axis is nothing but the exact position which is held on the particular beam. So here the both critical neutral axis as well as the actual neutral axis lies equal. which is nothing but balance section. Whereas the same case in under-reinforced sections, the critical neutral axis is higher than the actual neutral axis. In a sections, what we are proposed, in what we are built, that location, the actual neutral axis is lesser than the critical neutral axis. This denotes that there will be excess portion of tension zone, there will be very lesser portion of compression zone. So, which creates the failure in the steel because it is having higher area, but the amount of steel is exactly same as balance section. Here 3 numbers and the same 3 here, but the area required to cope up the additional tensile stress is higher. So in that case, the ductile failure will occur. The steel becomes failure, and the over reinforced sections, the actual neutral axis, which is getting higher than the critical neutral axis. In this diagram itself, we can see that in the compression zone, the area is higher compared to the tension zone. So here the brittle failure will occur and the concrete will fail first. And the second point, so as I said earlier, both compression and tensile permissive stresses are equal, whereas in balance sections. In under reinforced sections, the stress in steel is higher than the stress in concrete. The reason because the area of the tensile zone is higher. The reason because of that, the stress in steel is getting higher. And whereas for over reinforced sections, the area of the concrete is higher, so the concrete stress is higher compared to the steel stress. And next one, the actual compressive stress value, which is equal to the formulated compressive value. So here, the actual compressive value is lesser than the formulated compressive value. The reason because the compression zone value area is lesser, so the actual value is lesser than the calculated one. But whereas here, the actual value is higher than the formulated one. And next one, actual neutral axis, which is equal to critical neutral axis, as I said earlier in balance sections. Here, the actual neutral axis is lesser than the critical neutral axis, whereas in over reinforced sections, the actual neutral axis is greater than the critical neutral axis. And here, the both compression and tension zones are fixed, so there won't be any deviations. That is fixed compression zone. But whereas in under reinforced sections, the compression zone getting shifted above because it is getting lesser, it is getting shifted above. And here in over reinforced sections, the compression zone getting below. The reason because the area getting higher. And next one, the lever arm value. The lever arm value is constant for balance sections, whereas the lever arm value is increased in under reinforced sections. The reason because the value of actual neutral axis is getting reduced compared to the critical neutral axis. That's the reason the value of lever arm getting increased. Here, the value of Z value is decreased. The reason because the X value getting higher. So when compared to this, when substitute that formula, the value of Z also getting lesser. And the steel required for under reinforced sections is lesser compared to the balance sections. First, the steel fails before the concrete fails in under reinforced sections, whereas in over reinforced sections, the concrete fails before the steel attains failure. Some of the important limitations நமக்கு IS 456 2000ல தந்திருக்காங்க. So for singly reinforced sections அதுக்குல ASD maximum reinforcement எவ்வளவு ப்ரொவைட் பண்ணனும் அப்படினா 4% of gross area. So gross area அப்படிங்கிறது nothing but breadth into overall depth. So இதான் நமக்கு gross area. So maximum area of the steel provided is 4% of gross area. So this is singly reinforced section. இதே doubly reinforced section இருந்தா 4 plus 4 8% of gross area maximum area of the steel நம்ம provide பண்ணனும். Whereas minimum area of the steel எவ்வளவு provide பண்ணனும் அப்படினா 0.85 divided by Fy into B into D. So இது எல்லாமே நமக்கு IS 456 2000ல provide பண்ணிருக்காங்க. So minimum area of steel 0.85 divided by yield stress into breadth into D is nothing but effective depth. So the effective depth எப்படி calculate பண்ணுவோம்? Effective depth equal to total depth minus effective cover. effective cover, and clear cover value. So clear cover nothing but the extreme end of the section to the extreme end of the steel sections. So அதுக்கு இடைப்பட்ட இது தூரம் தான் clear cover. So clear cover அப்படிங்கிறது nothing but so நம்மளோட reinforcement இங்க ப்ரொவைட் பண்ணிருக்கோம்னா clear cover அப்படிங்கிறது the end of the reinforcement to the end of the section, this is called clear cover. For beam this should be 20. Okay, that's it from today's video. So in the next video we will see the single reinforcing section by using limited method. So do subscribe and please put a comment. So if you need any further informations, we will also provide in the next video, and the expressions what we have seen in the today's class, we will see the related questions which was asked in the previous examinations. So along with the limited method design. Okay, thank you.